So we turn now to techniques in single molecule fluorescence. These allow one to extract information beyond the limits of conventional optics. We've talked before about the wavelength limited resolution of a conventional lens, but let's elaborate that just a little more now. If there is some aperture here, A, and a focal length F, we can define an angle of this cone of light theta, and then the numerical aperture of the lens is defined by n, the refractive index of the medium sine theta. So given the limitations on how small one can make a focal length and the size of an aperture, the resolution, it turns out, is given then just by the wavelength of light over twice the numerical aperture. This is typically half a micron. By using blue light, very high refractive index medium, and the largest possible numerical aperture, it's possible to get down to maybe 100 nanometers or so. So what about fluorescent techniques and how do they work? Let's backstep to describe the process of fluorescence. So if you remember, I described to you the effect of thermal fluctuations on some energy minimum, which we'll now take to be an electronic state, as giving rise to a parabolic distribution of energies. This is a classical concept. If one solves the problem of a particle in a parabolic box, one comes up with a series of allowed quantum states, which I have sketched here, and these are referred to as the vibronic electronic states of a molecule. So if one has an electronic state that is the ground state, in practice it is many states reflecting the vibrations, and then a first excited state will also have vibronic states. And so electrons can make transitions from these ground states to any of the excited states. Fluorescence occurs when electrons decay by non-radiative transitions to accumulate in this lowest excited state here. And so there is then a considerable amount of light intensity when these then decay back to the ground state to emit radiation. A diagram like this, by the way, is called a Jablonski diagram. It's also possible for electrons to go into classically forbidden states if they interact with something in the material that flips their spin and allows a triplet state to be formed. But this is a very rare event. This is the phenomenon of phosphorescence, which is highly delayed emission of light, and it's how radioactive wristwatch dials have been replaced these days. So let's take a look at what an absorption and fluorescence spectrum looks like typically. Remember, I said that the absorption energy comes from transitions from all of these vibronic ground states into a manifold of vibronic excited states. And so the absorption line width represents the density of states of both the ground state and the excited state, and it peaks where those densities of states are a maximum. Now, the fluorescence, on the other hand, represents an accumulation of electrons at the bottom of the vibronic excited states, and so they map out a lower energy set of transitions, which also peak where the ground state density of states is highest. The result is then that when one plots the absorption or fluorescence intensity as a function of wavelength here, then the absorption might look like this, and the fluorescence might look like this. They tend to look mirror images. There is a shift owing to these transitions in the excited state here to longer wavelengths for the fluorescence, but they tend to look like mirror images of one another to the extent that the density of states in the ground state contributes. Single molecule fluorescence has become possible in recent years. The reason is that the lifetime associated with fluorescent transitions, which basically comes from the time it takes these excited states to decay down and populate the lowest vibronic state is on the order of a nanosecond. So this means that if I take a molecule and hit it with a very intense electric field, such that just as soon as it decays, it can be re-excited again, I can have one molecule emit about 10 to the 9 photons per second, and that is quite a measurable signal. Increasing the electric field helps to the extent that one can approach this limit of 1 photon every fluorescence lifetime. The principal limitation, though, has been dye chemistry, because a dye in its excited state is reactive and therefore tends to degrade in an environment with oxygen by reacting with it. However, modern dyes have been developed that are quite stable at very high fluorescence yields. So with these techniques then, one can detect a single molecule passing through an intense laser. This ability to detect single molecules, it is worth remembering that our statements about fluorescence behavior on average are quite different when we look at single molecules. So when we think of individual transitions now, they can occur from anywhere in the manifold of ground vibronic states to the manifold of excited vibronic states, and ditto for the fluorescence. So now the transitions we must think of as occurring in a single molecule, which will cycle through its fluorescence states at a rate that at a maximum can be the fluorescence lifetime, and each photon will come up with a very sharp energy. So this idea then of a distribution of absorptions that might look like this and a distribution of emissions that might look like this in terms of wavelength, in practice becomes absorptions that may lie anywhere in here and a set of emissions that may lie anywhere in here. With adequate collection of data, one recovers the multi-molecule fluorescence distribution, but the data at the single molecule level is bound to be more noisy, with individual photons reflecting in fact very sharp transition widths.